I'm starting recording. And welcome to the Winds and Currents webinar. Today we have Joe Sienkiewicz from NOAA. He serves as the Chief of Ocean Application, the Ocean Applications Branch of the NOAA Ocean Prediction Center. And he's going to talk about winds and current challenges from an operational perspective. So take it away, Joe.
All right, thanks, Sarah, and I have to apologize to this community because I have conflicts at this hour, but I've tried to stay abreast as to the discussions and all. So I work in operations. So there's a template as to what I'm going to talk about. I'm going to go ahead and move forward with this, but I want to talk about the operational challenges, winds and currents, scale, and challenges to shipping. So we'll actually look at some ship tracks in some areas of interest, and even some descriptions from some ship captains of crossing the Gulf Stream, which is in our waters of responsibility. So let's see. There we go. Okay. So a little bit of context is when I say operations, meaning that actually the U.S. has responsibility, the WMO, the World Meteorological Organization, working with the International Maritime Organization, both arms of the UN, have divided up the ocean into Med areas. And the U.S. has responsibility for Med Area 4, which is the Western North Atlantic, and Med Area 12, which is the Central and Eastern North Pacific. So I have as an underlay there something called the Global Maritime Traffic Density plots that actually one of the U.S. agencies, the NGA, basically has put together, is contracted out. These are done monthly. This is June of 2021, just as an arbitrary, but what it shows is 1 kilometer vessel density over the month of June in 2021. So you can see where fishing is. Those are sort of the clouds of activity, and then also where the Great Circle tracks and the predominant ship tracks were existing in the month. And these do change with time during the seasons. Winter would be a little bit less dense, say in the northern routes across the North Pacific. So why do we do this? And the U.S. contributes. We're one of the Med area providers. It stems back to Safety of Life at Sea Convention, actually the 1929 version of SOLAS, Chapter 5, Safety of Navigation, and its Regulation 4, where basically it says a contracting government, of which there are many, there are 16 that contribute to the Med area forecast globally, to warn ships of gales, storms, and tropical storms. And there are other parameters in there. So that's actually sort of like the overarching document. The International Maritime Organization, Maritime Safety Information resolutions are actually where the language is defined as to sort of what more definition as to what actually the Med area responsibilities are. And then on the bottom, I have as to how this is done. The regulations basically are from the WMO with what we call Pub 558, which is a guide to meteorological services. So with that sort of our sort of foundational documents as to what we follow, that helps to ensure that there's a standardization for marine weather services around the globe. Because as you look at the basics as to where vessels are, they're global travelers. And that you can see, look at the density. If you look south of Mexico and look at the density of the various tracks going to and from the Panama Canal. So again, a reminder that ships are global wanderers. So we're a warning office, and meaning that we actually issue gale, storm, hurricane force warnings. WMO has put a recommendation in the most recent version of Pub 558 that we start to consider warning for dangerous seas. Now, this is a winds and currents seminar, but we're struggling in other Med areas. We're actually working with Environment Canada. What is meant by dangerous seas, because it becomes vessel specific. So we have some thoughts that way, but one of them could be wave current, wind, wave, and current interaction. So let me keep going here. Okay, just as an example. So this is wind wave, which is wind current manifesting itself as wave interaction. This is actually Plum Gut. I was actually riding the ferry. This is a picture I took some years ago from Long Island over to Connecticut. And there's a rather restricted area between Plum Island and the North Fork of Long Island, which the ferry takes off of Orient Point, where it's known, it's great fishing grounds because the water is churned up. But this was just in a day when a northwesterly wind and an incoming current basically opposing each other. So a very narrow, well-defined area of enhanced wave action. So that's one example. And oh, whoops. There, and this is the nautical chart that goes along with that. So that green and red buoy that you see there in the lower, in the mid left, basically is you're looking at an area where it's relatively shoaling. There's very strong current on the other side of the buoy. The ferry was actually about, I think, where the W is in Midway Shoal, because it's a relatively shallow draft ferry. But it gives you an idea of the scale of some of the challenges, manifestation of wind and current interaction manifesting itself in the way of waves. And I have one more. So this is a little bit better picture. This is the east end of the Cape Cod Canal, mid-September of last year. And this is about a 4-knot current. I was on a sailing vessel, a 60-foot sailing vessel. We were producing enough power for about 9 knots of passage. We were moving at 14 knots. So we would be 4 and 5 knots of current is flowing from left to right in this picture. And we're in the jetties about to come out into the Cape Cod Bay. But you can see we went through a very rapid transition of how wind current interaction manifests itself in the way of waves. This wasn't particularly hazardous conditions because of the size of the boat we were in. If we were in a smaller boat, this wouldn't have been quite untenable. And again, the transition zone, very, very, very sharp. Okay, so let's start in the lower right. And I'm gonna, I hope I don't insult anybody by saying this, but I sort of grew in this world. This is an AMSA2 image down in the lower right-hand side here, which is wonderful. 25-kilometer resolution of SST, all weather, certainly through clouds. Obviously, the clouds being a challenge for infrared sensors from geostationary satellites or polar satellites. But a reminder that the representation in the lower right is exactly what that is, a 25-kilometer resolution. So if we take a look now at the thermal image of the Western North Atlantic, say, for instance, starting off of Cape Hatteras in this area and looking at the west wall of the Gulf Stream and all the filaments of warmer water and how basically this is repeating over and over again, but your eye is attracted to the structure and realizing that that structure has current. Not only the core of the Gulf Stream, but certainly the filaments that are coming off of the Gulf Stream. There's an eddy to the northeast of Hatteras. If you look farther north, there's actually a warm ring to the southeast of Long Island that just gets exposed towards the end of the loop as it's looping through because of temperature contrast is actually producing cloud over the eddy. And you can basically get a flavor, and this is a 2-kilometer resolution of the what the structure and the complexity of the ocean that we're trying to understand and analyze and predict. Never mind the related challenges of interactions, such as I just demonstrated on very small scales of a couple of images. But the great thing is we have tools now, for instance, a 2-kilometer resolution infrared imagery, that at least we're getting an appreciation for the structure and the challenges of the ocean surface. And I guess my way of deferencing, and the right-hand side for most of my career, the AMSA 2 image, that's kind of what meteorologists consider the ocean to be. And obviously it's not, and it's great to be able to kind of have the imagery that we have, but also kind of demonstrates the challenges of scale, both temporal and horizontal resolution as we're moving forward. Let's see, come on. Okay, so I'm going to talk specifically because the Gulf Stream is in our waters, and I'm going to talk about several of these and give some examples. One is wind and current interaction, a function of gradient of current and strength. Another is basically the influence of the underlying ocean on the atmosphere and generating basically and maintaining an atmospheric front, thermal front, which is a natural phenomena. It's an area of enhanced baroclinicity, low-level baroclinicity, atmospheric. It's a focus area for cyclone development and for intensification. And also, even going back to my master's work way back in the mid-'80s, was focused on thunderstorm activity. And that actually can play at times into intensification of extratropical cyclones, where we've actually seen associated with the Gulf Stream front, meaning the atmospheric front, we've actually seen mesoscale convective systems develop and help enhance the intensification of extratropical cyclones. So very active area weather-wise, but also obviously oceanographically. Scatterometry really helped us to kind of better understand this stratification of the atmosphere and relationship with the underlying ocean. And I'll show an example or two of this afterwards, but cold air over warm water, we tend to have gusty conditions and hence backscatter. So back to the quickscat days, we definitely could see the footprint of the ocean being manifested in the backscatter, and therefore in the ocean thermal structure, surface thermal structure, and being manifested in the backscatter and the wind field. And warm air over cool water, stable and limited mixing. And in fact, Jim Edson gave a talk at AMS this past year and talked about the height of the inversion. And I know from actually talking to sailors, at times the shallow inversion can be relatively shallow. It can be 10 meters in height. It can be, maybe 20 meters at height. But the important thing is the boundary layer basically decouples from the ocean surface, or partially decouples from the ocean surface at times. We met with, I'll share this story, we met, oh boy, back Ernesto Rodriguez, Paul Chang, Zorana Jelinek, and Rob Gaston. We went to Boston and talked with world ocean racers that had come into Boston. And this was maybe 2008, 2007, somewhere around then. Anyway, and they talked about coming into Boston, where they were they were sailing in cool water, warm air, warm advection, southerly wind. The ocean surface was glass. They were moving at 25 knots, and they were driving their 100-foot tall mast sailboats off of the top 25 feet of their sail. So they were in the inversion and below the inversion, except for aloft. And they said it was just fantastic sailing, flat water, where there were no waves, no ripples, no capillaries, and just, in perfect sort of conditions, but actually just driving off the, as their top of their sails and masts were poking up through the inversion. And the last one is swell ducting and wave energy being trapped. And I have a picture of this. It's a function of gradient of current and strength. So therefore, all of these things, and in particular with waves, wave current interaction, basically are all requiring the observation and understanding of the complexity of current. Whoops, come on. I have a hair trigger on my mouse. There. Okay. So for examples. One is in the upper left is wind versus current. This is a kind of a well-known picture that Paul Chang took many years ago from the NOAA P3. The Gulf Stream is in the lower right waters, and to the upper left is waters north, the cooler waters north of the Gulf Stream. And the roughness, the white capping you see there with a relatively sharp boundary is wind against current in a northeasterly flow. And this was somewhere southeast of the Virginia Capes in the stream. The right-hand one, this also is a famous picture because it basically has been used in rogue wave talks. Andy Chase, who just retired from Maine Maritime, was aboard back when Gulf Oil existed and had tankers. This is a Gulf Oil tanker loaded, coming up the coast, was off of Charleston. There was a large storm to the southeast of New England. They were not in the storm conditions. And basically they kept seeing waves breaking on the horizon. And they actually were wondering if what they were seeing were whales breaching. But no, they were not whales breaching. They were wave breaks. This is about a 60-foot wave. So the ship, being a loaded tanker, did not lift in that wave, basically went into the wave. Some of the piping that you see in the lower part of that image was smashed. The foremast was bent back. The wheelhouse, of which Andy and a colleague who actually took the picture, an engineer, were on the bridge wing, on the starboard bridge wing, flooded. And so did the wheelhouse. So in other words, the water came up and was able to get about the height of where the camera is here. Not necessarily, well, green water may spray and all. Anyway, this is a case where trapped energy, distant storm, swell propagating, and focusing in the stream, producing what we consider to be a rogue. I never like using the word rogue wave, but anyway, enhanced wave or focused wave trapped in the current and refracted by the current boundary, the gradient. And the bottom two have to do, they're actually this similar time. SST in the lower right, it's a 24-hour composite, and on the left-hand side is ASCAT passes. And what seeing here is if you look back and forth, you'll see in the lower left, say for instance, where this dark green area and there's some yellow in here, which are gale force winds. The dark green are near gale or subgale, near gale on the Beaufort scale, and get an idea that you're actually seeing the wind field as inferred by scatterometers actually giving you an indication of the sea surface temperature and temperature gradients lying underneath. So you're actually seeing the footprint of the SST being manifested in the wind field through stratification. And I know Dudley Chelton's done a lot of work on this. But just to give you an idea of what this kind of looks like. So these are the sort of the challenges that we have off the East Coast, and these exist, all throughout the global ocean in the mid latitudes in particular. Okay, so a more zoomed in example, this actually goes back to the Quickscat days, where a southerly flow, so warm air advection, a high somewhere to the east, northeast of Bermuda, off of the east coast of the United States. These are our offshore zones as they were back in the day. And you do see some gradients of wind speed. And also there's an area here to the on the southern boundary of the New England waters where there's near gale, 23 to 27 knots, and then near gale 27 to 33 knots. In there, and again near gale extending out to the northeast in a rather defined fashion, and much lighter winds, lower wind speeds to the southeast of New England. And let me go on to the next. There we go. So this is the sea surface temperature composite from GOES at the time. This is a 6 kilometer SST, so it's a little coarse, a little noisy. But if you remember the wind field, you'll actually see the north wall of the Gulf Stream here, shelf break front up to the north, and you can see the cooler waters extending well south, almost to south of Montauk, extending westward in here. And I'm going to go back to the image there, so you can see where I was just pointing. So you can see how basically the wind field basically is portraying basically the underlying SST. So anyway, so that's one of the challenges we have. So that's wind. Now let's go ahead on. So here's an example of an incident that happened several years ago, January of 2021, late January. Eastbound ship, a small break bulk, well, not break bulk, but general cargo or bulk carrier heading from Norfolk to Tunis, to the Mediterranean, and was struck by a wave in the Gulf Stream. There were 4 crew injured, 1 fatally. At the time, there was a cyclone, and that's on the right-hand side here, an intensifying cyclone of storm force intensity, northeasterly flow across the Gulf Stream in that area, and basically generated conditions such that the ship was the fact that they were injured. I don't know if they were in the wheelhouse or actually working down on deck, but they had to divert. The ship did have some damage and was in Halifax for a period of time, so they diverted up to Halifax and then went on its way after about a week and a half or 2 weeks. But meanwhile, there were injuries and 1 fatality on board. And it gives you an idea of his altimeter pass is a little bit too far to the west, but at least it gives you an idea that they were relatively, these are in feet, so 18, 20, up to 25 feet just to the east of the vessel, Julia motor vessel. So 1 indication, and no indication earlier than that in the track of the ship. I'm going to show you another vessel. Okay, this is a modern container ship, Overseas Orient Container Line ship Bangkok. Was outbound Charleston on its way over to the Suez Canal. And this is a modern ship, not very typical now as to some of the ultra large container ships, 13,000 TEU, thereabouts. That means can carry 13,000 plus tier equivalent units, or which are 20-foot boxes. So in other words, you can divide that in half for a typical trailer truck of 40 feet. So 6,600 ish. Containers of trailer truck size that it can carry, and a relatively deep draft vessel, 144,000 deadweight tons. So eastbound in a northeasterly flow, it came out of Charleston at 13 knots. When it entered into the Gulf Stream, slowed all the way down to 5.1 knots to 4.6 knots. The assumption is because of seas, but seas with a wind being driven by a wind opposing the current of the Gulf Stream. So the vessel actually slows down as it enters the Gulf Stream. And so it's time lost, but they're slowing down for a reason. That goes back to sort of the language that I had up front, is our mission basically is safety of life and property, the code of our core mission. We also have a part in our NOAA language of enhancement, economic enhancement where we can. But this is safety, as we saw in the example earlier. So as the ship reached out of the Gulf Streams, returned back and was back moving at about 14 knots. So conditions are such with wind current interaction that the vessel had to slow down. This is not a small ship. This is a 366 meter long ship. They don't, at this point, they don't seem to be getting, well, they are getting a bit bigger lengthwise, but they are getting beamier and taller. So just one example. And these are the, come on, sorry for that, bouncing back and forth. This is the ASCAT's passes and gives an idea with the wind field thereabouts the time, with the gale force winds from the northeast, the stronger winds to the south with a low well to the south off of Florida. That gives you an idea as to where the type of winds there were in the area. And then I've got 2 altimeter passes here, and it's the one to the right. I can't remember what the time 1533, which is right here. That actually tells me which one it is, and I don't have my card in front of me that tells me which altimeter, but it's not one of the Jasons. My guess is it's yeah. Anyway, I can't remember which one of the Sentinels. But seas and actually the ship was a little bit to the east over where my cursor is. So, but seas farther south in the low 20 foot, 7 meters, 6.5 meters to the south. So anyway, but we don't get an observation exactly where the ship was at the time. And that's the single pass. And those are the observations, typical distribution that we have for buoys. The green numbers are actually significant wave height. So, again, showing what's relevant, what observations are where the buoys are, but unfortunately where the need for information, there aren't any buoys, and we all know the challenges of that. Trying to moor in a strong current is a real challenge. So, and this is the NCOM current model showing an area of potentially 2.5 knots off of Charleston, northward flowing current. Whether or not, and this is a challenge, is timeliness, whether that's fully representative of what where the vessel was going across, as an example. I guess the one to take away from this is scale really matters when it comes to current, and gradients really do matter. So let me go ahead on. This is another example. This is a westbound ship. This was actually in the U.S. on Thanksgiving Day back in November of 2019. And I actually had an email conversation with the ship and with the vessel afterwards, the incident. But that's actually observation from the ship later on, after actually it had gone through the cold front and passed through the cold front with strong gale conditions at that time. This is the track of the ship, 18 knots as it was approaching the Gulf Stream, slowed down to 11.9 knots, and then was able to continue on, accelerate a little bit once it got into the stream and conditions kind of calmed down. You'll see that in the next write-up. So just for a picture, that's the ship, not a small ship. So this is from Captain Chris Kavanaugh. So we encountered the Gulf Stream around 28 November, 11Z, and the location and the swells were confused and massive. Water temperature was around 24 C. Once we got through the south wall and into the stream, the sea became more predictive and uniform. Winds were a steady Beaufort force 10 to 12, and at times exceeding 100 knots, veering from south-southwest to north. So they basically were ahead of the cold front when they entered the Gulf Stream, in the low-level jet, in the southerly low-level jet. And then you saw the observation of 35 knots where they were back in the cold air once they had got into the Gulf Stream. So they were in the south-southwesterly flow when they entered into the stream. But even so, the fact that the seas were massive and confused. And last one I have here is actually, we had a student in 2019 who dissected vessel transits of the Gulf Stream and matched them up with Navy analysis of the stream that we use. And basically, we were looking to see just the vessel behavior transits. And this, again, was a low pressure system that was passing the area. So winds going from northeast to north. Actually, they got into southerly for a period of time. This is a 250 meter tanker and was most likely returning to carry on a load. So it would be what's known as in ballast. And you can see how the ship in green, the colors indicate the speed of the vessel. So greater than 12 knots is green. So the ship enters in the upper right-hand corner. As it approaches the stream, it turns more subtly and is moving between 6 and 11 knots. And then actually, as it enters the Gulf Stream, slows significantly between 2 to 6 knots. And actually, for one point, is actually less than 2 knots. In essence, the ship was hove to for a short period of time, and then got back on its way as it was moving slowly, and then continued on its voyage southward. So a tactic of coming through the Gulf Stream in significant conditions. So for this, the last slide I show you. So we did this study from the 28th of December of 18 to April 2nd of 2019, looking at collected a bunch of ship transits across the stream. And then we divided them up on the impacts, meaning reduction in speed. So the next, I'll transition to this in a second, but what you're going to see is the location of where vessels were operating at 60 to 70% reduction in their normal speed. So for instance, a 15-knot ship would have been moving at, say, 6 knots, 60%, between 4.5 and 6 knots. So I'll just let it speak for itself here. So let me go ahead and so that's all the locations where vessels were significantly reducing speed. And I think it's a pretty clear message that it relates fairly directly with the Gulf Stream. We learned something, and I'll show this. This is cluster out here to the southeast of Nova Scotia. So what kind of that cluster is there for one reason is vessels that are required to carry dual fuel, low sulfur and high sulfur fuel, have to transition from high sulfur to lower sulfur, which is less efficient, more costly as a way of looking. So there's an economic reason for this. Is when they cross into the EEZ, to a nation's EEZ. So you're required to change fuel types. So a way to do that, a way to sort of not get around that, but to deal with it is basically to stay out of EEZs or plan your voyages to be in an EEZ as short a period of time. For instance, if you're going on a Great Circle route and you come out of the Columbia River, you typically go directly west, get out of the EEZ, and then start your Great Circle track. The traffic densities show that. This area southeast of Nova Scotia actually is a choke point because it's the boundary of the EEZ. It's also where the Gulf Stream and the EEZ touch. So in other words, ships, there's a cluster there, higher density of speed reduction because it's a combination of a high traffic area because of the behavior, but then also because it's where the Gulf Stream matches that area of coincidence. So something we didn't know, but when you look at density plots now, it's very clear that vessels avoid the EEZ. And I'm not putting a spin on that, negative or positive. I'm just saying this is what the data shows, and so does the traffic density data. So it's one area where the periphery of the EEZ and the Gulf Stream marry up with the ship tracks coming across from Europe or going over to Europe. So wind and current. So we're in an interesting phase where there are many discussions about the future and the requirement for reducing the carbon footprint. One of them, one consideration is alternative fuels. And I'm not an expert in any of this. I have read the regulations that have been put forth by the IMO and the continued discussions. But the other is propulsion enhancement. For instance, wind turbines aboard a vessel in order to enhance, or even as a prototype Ocean Bird there, basically having wings to help propel a vessel, whether it's assist or actually the propulsion method. it sure seems like, the work of Maury and others, basically from years and years and years ago, may come back to life a bit. In other words, wind and current as propulsion means may come back into more favor over time as an alternative. So in relationship to this effort, there may very well be a direct relationship. Current obviously being, you get an assist. On my end also is a meaning in the mission that I work on is a concern about safety at times, because there have been incidents with wave interactions in current. So I just thought I'd bring that up, that there are certainly discussions globally, and can look up also, and see images such as this as to what prototypes or considerations for what the potential is for going forward. But it would mean that wind and current will have more of an economic influence than perhaps that it does right now. So something just to consider, going forward. So mission, a core mission for the Met Area providers, safety of life and property. And obviously, wind and current interactions play into that. I focus primarily on the weather timescales because that's my office's responsibility. Day 5, out to day 5, out to day 6, 7, 8, and that time frame, and not on the relationship necessarily with climate. So just to be clear, and I think I kind of certainly demonstrated that. And I found it in prepping for this, and in fact, Sarah, when we talked last June, it is challenging to address this in the context of wind and current, and not include waves in that. And that's not a negative to this mission, because I think what it stresses is how challenging how to this date, without a specific mission in order for global current, we really are only, except for infrared imagery, which we don't have all the time because of the reasons that we have, because of cloud cover, that to really have an appreciation of current as resolution required, but then also gradients of current as to how sharp they can be, and representative, it alone, I think certainly this mission is well worth, and have fingers crossed, like everyone, that this moves forward. It doesn't diminish the requirement for high resolution and coincident winds and current. And so I just want to make sure that that's clear. I'm not advocating for anything. I'm advocating for winds and current. Ocean vector winds showed the example of ocean atmosphere interaction in the boundary layer, but then also ocean surface currents. Certainly search and rescue, set and drift is really, really critical. That especially in the short time frame of an incident, to try and determine potentially where, because over time your search pattern has to grow if you don't have the parameters. I mentioned about for current at representative temporal and horizontal scales, that certainly whether that's to be determined, at least that as needed for data assimilation, then also for analysis, for understanding where features are and how strong they are in the current sense. We inferred impacts via vessel actions, but not the conditions. So we tend to look at vessels, but we don't know exactly what the conditions are that are causing the behavior. So you can make assumptions that it's a combination of all three, wind, current, and waves, but we really don't know that. The only one really know is the example of with the injuries, where it was stated as to be a wave interaction. We're also at a time we're transitioning to fully coupled modeling systems, and we need information in order to anchor those: data assimilation, verification, and validation of wind and current parameters. And then I also mentioned with the graphics of the sort of potential of what vessels may look like going into the future. But if that appears to be the direction that we're going, then improved wind and current observations and prediction are really going to be needed, whether it be the direct propulsion means or alternative means or additional means. So I'm going to stop there and ask any questions.
Well, thanks, Joe. Questions? I'll just mention first, there were some comments in the chat that it's worth noting. Deirdre Byrne pointed out that the NOAA Lab for Satellite Altimetry supports the development of blended ocean surface currents, which merge large-scale wind-driven currents, surface geostrophic currents, and currents deduced from SST imagery. So I don't know if you want to say more about that.
No, I'm glad to I mean, we've always considered it's not one thing, not necessarily one thing or another, and this is sort of hard, is especially what is it you need to do your mission, and as we've grown and operationalized, say for instance scatterometry, it doesn't mean that it becomes less important. In fact, we've had sort of internal discussions that there's a very high emphasis on in situ observations with different means of observing systems. Okay, and that seems to be kind of the flavor of the month, or whatever is sort of a phase that we're in. But we can't take for granted existing systems now that we're going to have them in the future. We have to include those in the conversation. Meaning scatterometry has become for our forecasters, and I know in other parts of the world, same thing, is we look at every pass. We know we've learned things from the data. We know more about storm structure than we ever kind of imagined in the say 20 years ago or 25 years ago or more. And it actually is interesting that something that sort of got overlooked in all the examinations and all the studies of rapid intensifying extratropical cyclones, they didn't really look at storm structure. They didn't look at wind structure. Well, they didn't really have the tools to do that. So except for by flying an airplane or dropping buoys, but scatterometry filled in the holes. Just as an example. So I agree, contribution, multiple sources of information in order to really get the best starting point for data assimilation, for numerical models, but then also for our understanding on the science side.
Great. Rick Danielson noted that the speed reduction might be associated with voluntary avoidance of right whales, at least on the shelf.
Could be, that's true, and we didn't have a way of making that distinction. We didn't go back, but that's a very good point. I live in Maine, so right whales are a hot topic, to say the least. But yes, I appreciate that, and that's a good point. And we didn't really have a way of really determining the behavior. But you see that much of what we were seeing was actually down in the stream.
I guess I wondered, do ships slow down at all to change fuel?
Yes.
As they cross the EZ?
Yeah.
Does that show up in a meaningful way?
Surprisingly, it didn't, except for in that one location southeast of. But we did look at the data to see. We did actually dissect every vessel, so we did look to see, and they matched up very, very well with the stream, with the Gulf Stream.
That's an impressive behavioral pattern.
Yeah.
And Melanie Fewings has a question. Melanie, do you just want to go ahead and ask?
Oh, sure, I can do that. Hi, Joe, good to see you. I was wondering, this was more of a question about the proposed Odyssey mission, but I was wondering, we've had these conversations in the Ocean Vector Wind Science Team meeting sometimes when you've been there, I guess, but it seems like NOAA is still not planning scatterometer missions of their own. And I was wondering if they have talked about contributing to Odyssey besides the way they already are doing through NOAA Fed's time, who are participating in the proposal writing.
Not that I'm aware, but I'm not also in those conversations at that level. I do know on the Weather Service side, there is an increasing interest in scatterometry.
Mm-hmm.
Now, how that manifests itself, we're, and this is the challenge, is Weather Service, we're the customer. So that we've written requirements, we've done everything that we can that points towards high resolution, frequent, basically a constellation. And the next step is always the hard one. But there have been discussions internally with Weather Service where, if you just beg the question, we're a user, we advocated for this, and there does seem to be interest at just above my level that why don't we have a scatterometer? Why aren't we contributing? So our Office of Observations, we have these portfolio structures and observations. Basically, they've started to have conversations. And wanting to understand, NESDIS has some interest. Whether there's an opportunity on the funding side, that's a whole different thing. But I don't think there's a verbal commitment at this point. But go ahead, Melanie.
Yeah, I guess when I first joined this community sort of 10 years ago or something, I feel like that was a topic of conversation, and it seemed like politically NOAA had decided they were not going to fly scatterometers. And so I was just wondering if you felt comfortable sharing anything you knew about how the politics might or might not have evolved since then. Is this something we should pursue? I'm just naively asking these, should we just start calling people in NOAA and pestering them to contribute to Odyssey? I don't know. Would that be a bad idea?
No, I don't think it would be a bad idea. No, not at all. And in fact, I'm probably guilty of not, taking part as much as I should. It's just, all of us have conflicts at this hour. I think on the operational side, I think we're missing a little bit of opportunity in order to be a little bit more broader focus as to what's coming. And I have to admit that I'm challenged time-wise, but I can't take scatterometry for granted. We can't, and that at least I've been clear in our organization is you can't, don't advocate for this without advocating that. Have it all in the same sentence. Because the oceans, no matter what, they're data void. Comparatively, they're data void, and there's so much that we have to understand. Yeah. Anyway, thanks, Melanie. Good question. And yes, I still have scars from back in the mid-2000s of advocating. So
I know, and I know almost nothing went on there. So I'm just naively asking if we should be bringing it up again, or if it is pointless, or people have already had these discussions and I just don't know. So thanks for the information.
Okay, thanks. Yeah, go ahead, Sarah.
Deirdre Byrne has her hand up.
There I am. I see Paul Chang's also on the call, and he's also in NESDIS, but in general, NESDIS doesn't invest in what they consider to be experimental platforms, right? They want a proven technology where they can invest in a whole series that are going to be the same. So that's just a general rule. I don't know anything specific about Odyssey, but now you can then point out things like Jason, which was a proven technology, and NESDIS stepped away from it anyway. I'll just close my mouth there. Yeah, so I would be very surprised if NESDIS supported Odyssey. We sometimes have an uphill battle to even get research funds in NESDIS to try and develop products using experimental platforms like SWAT, because they're like, well, there's only one of them. Why bother? And we're like, well, because that's the first of what's probably going to be many, right? We can see that. We as scientists in the discipline can see that coming. So Paul may want to say something else. I'm not an expert on scatterometry at all, but that's just the kind of That's the landscape that we work in. They like a proven technology. They want to see a series coming out so that whatever we develop can be operationalized through the series. And sometimes experimental platforms in particular get short shrift. The scatterometry is a really interesting question because that's definitely, I mean, in general, scatterometry is not experimental. So, you know, that would be an interesting door to knock on.
Yeah. Yeah. Thanks, Deidre.
Following that comment, Rick Danielson asked in the chat, and Rick, maybe you want to go ahead and ask this.
Right. Yeah. Hi, Joe. Yeah, the great presentation. I love the connection with the users. The bespoke sort of forecasting issues are there, and they're really valuable. But the forecasters in the middle. I mean, some forecasters are ready for SWOT, for example. I just want to know if you had a sense of people being ready for SWOT, because that's a kind of analogy for Odyssey.
Yeah, so SWOT would be, at least in the near real time, would, as I understand, would be the NADA data. You know, so similar to what we have now from on the science level, that will be sort of a different use, sort of behind, you know, in our world anyway. You know, lessons learned, kind of like the way we started looking at SAR wins, just more to kind of start to understand the difference between the resolution at 12.5 kilometer that we get from the ASCATs, or even a 2.5 kilometer that Paul Chang's shop produces, versus the very, very high resolution to look at wind features, to see how the wind actually manifests itself, you know, on the ocean surface. So we could use SWOT in that sense, the science level data, at least to get an idea of what's representative. You know, that from what I understand, at least as far as in NAWIPS and AWIPS, is we're looking at the NADA data as being the first, as to what we'd have available, and then we'd have to work through as to how we're going to see the other data.
Yeah.
So Eric and I have, Lilia have exchanged about that. We don't have necessarily a path forward yet, but.
Okay, nice.
We have a couple of hands up. Marcos, you want to go ahead?
Yeah, can you hear me?
Yeah.
Hi, Joe. Nice presentation. It's good to see you. Actually, we haven't seen each other for a while. No, I guess that may be part of the answer, but I guess Paul will actually answer this much better than me. But part of the answer of the question on scatterometry and why the US stepped out at a certain point is that, I guess, an excuse was that you know, we had India and China joining the club, and as far as I understand, Joe, you can also get the Indian and Chinese scatterometer wins, at least through the EUMETSAT OSI stuff, right? So you're getting those data or not?
We so far we have not India. We did in the past with India. We've never been able to bring Chinese data into our systems.
Oh, okay.
So,
okay.
Yeah.
So then that's not the full story. Yeah. But yeah, I guess, well, India is now launching a new satellite, probably Paul will say more about this. But yeah, we shouldn't use that anyway as an excuse. And I guess when you plan, you know, constellations for the future, in the end, you have to agree. All the, let's say, the agencies have to agree on, you know, what the planning is in order to make sure that we still have scatterometers. And of course, if we can cover the whole daily cycle, that would be great. And we still have some missing spots there, which I think will help a lot.
Yeah.
And going to the high resolution and SAR, I think that, of course, with only limited coverage, yeah, but we have a C-star, and Harmony C-star is like a SAR, but with a ASCAT type of geometry. So that's going to be actually, if it ever gets launched, hopefully, because it has to go through a selection process. Now it's a candidate mission. Will provide this capability. Yeah, so that would be really nice. And Harmony, in a way, also would do. And actually, Harmony will fly for sure. I think it's in 2029 or 30 or so, 31 maybe framework. So those are interesting missions to look at when we think of let's say high resolution and SAR, yeah, because then we have the nice viewing geometry that helps us really tackle the wind vector plus the currents. So we have both, yeah, in the same pot. So that's really nice. And I leave the floor to Paul, who I'm sure will give a nice perspective on what NOAA's involvement in spectrometry can be. Thanks.
Thanks, Paul.
It's too much pressure, Marcos. Great talk, Joe. You always have the best examples. I think, I mean, what you said about, Weather Service has done a lot for getting the requirements down and all that, but I think the politics have changed a lot since the mid 2000s or even the last decade. And as you probably know, NESIS has sort of moved into this, or trying to move into this more portfolio system like the Weather Service did, where everything isn't necessarily goes and JPSS centric, which leaves an opening for them to start considering other things. So, I would, keep encouraging, the people at the next level up over you and so on to keep, asking the question for the people in NESIS that are up above me to reinforce those requirements and say, hey, why doesn't NESIS do this? Why don't we consider doing this? As Marco said, yes, there's a lot of scatterometers. Well, there's a number of scatterometers up there. And I know back in the mid 2000s, NESIS Weather Service decided they were just going to leverage other agencies' missions instead of pursuing its own mission at the time. But, their really only solid partner is UMETSAT. India, they did just launch OceanSat 3. And notionally, I think there's plans, but nothing sort of, cemented in the rock like UMETSAT's plans. And, as you said, China's off limits. I mean, politically, there might even be an opening because of, China has more data than the US for certain applications. So maybe that's something that can be used. And then to, I guess, Melanie's question about the research side. I mean, that's one thing that's internally the NESIS has struggled with, is how to, it doesn't really have a formal mechanism by which to, in advance, try position itself to leverage research missions like the ones out of NASA. I mean, there's not a formal way to do that, which is a problem, but that doesn't mean you shouldn't. If you know people at higher levels in the organization, it doesn't hurt to go knock on doors, make calls, and ask them why aren't they should be paying attention to this mission or that mission, because things are always changing as far as the political environment. And then I guess lastly, I'll just leave Joe. We got one. I haven't talked to you in a little while, so I'll use this as a quick.
Okay.
So we have this new ASCAT high res product that we're just about ready to roll out. That's it's gridded in the order of a couple kilometers. Probably effective resolution is of course a little higher than that, but it's so I think of it a coarse resolution SAR data. We're kind of be able to get into the coastal region and the ice regions, and we're updating the model function to do a better job on tropical cyclones. So Marcos will probably be interested in that too once they're ready with that. So otherwise, I'll leave it at that.
And thanks, Paul, Marcos. Actually, I kind of miss all of you. I mean, just the way life has gone. It's pandemic. But I missed our annual meetings. Wherever they were. Paul, we have an intern this summer who's actually going to be setting up a way for us to actually make an input as to where we want to see high resolution winds, whether part of it is a goal in order to do the request for SAR processing, but then also we could use that for, so we've got to reconnect probably in the next month or so to see, because that's one of the problems we have is basically where because the processing is takes time, where is it of interest? We're very much interested in high winds and high wind structures. So we need to finally get our act together at having a process so our forecasters could say, here is a center of a wind area anticipation where we want to have high resolution processing, or if there's a SAR opportunity we could do. The SAR is different because it's like several days you have to plan things, and that's a little bit challenging on the predictive side to get the exact spot. So, but anyway, good points. And yeah, I've taken a couple of notes of a couple of individuals I need to talk to in my organization, because there is some discussion about certainly scatterometry. But anyway, I'd hand it back to you guys.
Well, I think we're at the top of the hour and we're going to have to stop. I'm sure we could keep going for a long time with a lot of great questions, and I'll urge all of us to email Joe with our questions and continue the discussion. I'm going to stop the recording. Thanks very much, everybody, especially Joe, for doing this.
All right. Thank you, everyone.
Thanks very much, Joe. It was a really interesting talk.
Okay, thanks.
All right.